Hello, everyone. Welcome on board. My name is Eric Espinosa. I work as a research assistant at the Fluid and Mechatronics Systems Laboratory at Linköping in Sweden. Today, I'll be presenting civil aircraft cost estimation using Wolfram technologies, part of the research being held. A little bit, the abstract general idea. The direct operating cost is crucial for airline fleet acquisition and in general project feasibility. This study will compare different DOC models with published data, and it will also analyze 2 aircraft in 2 sample missions. Finally, a sensitivity analysis will highlight the cost factors that will be the most crucial in the total DOC and a break-even price assessment. Little bit about myself. My name is Eric. I come from Mexico. I have some education background as a pilot, as a mechanical engineer, and I did my aeronautical engineering master's here in Sweden. My professional experience, mostly on education as a high school teacher. And then I did my internship at Wolfram Mathcore, the very talented team that makes System Modeler here. And something interesting that I would like to share with you all is how did I learn the Wolfram language? Well, in today's world, I use ChatGPT, and I learned it kind of in the same way that I learned how to speak. First, I was using it, and then I used it so often that eventually I figured it out. It's a kind of a change of paradigm I wanted to show you on how I learned the program by itself. So I have around 1 year of using it. No hard computer science background, but it's quite straightforward. And just to frame where this research is being held, there's part of 2 greater projects. One is called RITAS, which is a collaboration between the Swedish National Transportation Institute of Research and my university, LIU. And the other one is with LFB, which provides air traffic control services here in Sweden. They both involve sustainable aviation in Scandinavia. A little bit of it was also done when I was doing my master's thesis here at Wolfram Mathcore, working on the aircraft library. Now let's go to what's important, the global airline industry. This is an industry of 760 billion US dollars, and we take airplanes everywhere, and only the ones who have not flown probably think that it's a nice experience. I myself, a passionate about aviation, know it can be tedious sometimes in the airport. But as an industry, it's also very cyclical and fragile. You have these seasons of very high demand. We see it with the high prices we pay in Christmas and in summer. And then periods where it's really low. So good administration is needed. It's also very fragile. I think we all know an airline that has went bankrupt in our countries. Therefore, the economic and financial estimations are prime, not only for aircraft designers, but for airline operators. And this is a phrase that a professor used to say, how to make a small fortune on the airlines. You start with a big fortune. Because yes, it's a business, and mostly it's all about money, 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 like the ABBA song. And when it comes to the costs associated with operating an aircraft, they are not small. There are multiple categories. In here we can see that the indirect operating costs on the left, we see that it's a little bit more tricky to quantify. For example, promotion and sales, air traffic servicing, the lobbies, the lounges, those are costs associated with operating an aircraft. The ones that we can measure are normally the direct operating cost. This includes the categories that you might initially think about, the fuel, the pilots, the maintenance, and not only that, but the ones associated with owning an airplane, the insurance, the depreciation, etc. And how is this estimated? Well, we use models, of course, direct operating cost models. And I talk about direct operating costs because, as I showed you, it's easier to estimate. The thing is, as an aircraft designer, how do you estimate how much the aircraft will cost if the aircraft doesn't even exist? It's already difficult for the ones that are flying now. Imagine the ones that are still a concept. Not only that, but the models that we have available, they are very vast. There's a lot of them, and they mostly rely on statistical data. So no statistical data for a non-existing airplane, which is the case for the electric, hybrid electric, and hydrogen. So this leads to the question, from all the models available, which one should I use? That's where I'm going to try to put some light on. The little methodology that I followed was geodesic distance estimation using the Wolfram language. You'll see that one to get the distance from city A to city B. Then a mission estimator on the aircraft performance that will tell us how long did it take you to get, how many passengers it carried. And that information will be fed into the DOC models that we were speaking about. And we will compare this estimation that the models give with the actual published data from the manufacturers, which I'm spoiler alert, there's not a lot. Airlines are not eager to share how much it costs in such a competitive industry. Finally, there will be some sensitivity analysis on these models and a final study case on a Swedish regional airline, some data science or something like that. The two airplanes that were analyzed are the Airbus A320. You probably flew in one of them, or the 737 from Boeing, and the ATR-72, which are these propeller-driven aircraft for shorter regional missions. And the two missions that were flown for the ATR was the Stockholm-Gothenburg, because of course the study is in Sweden. And the one for the Airbus, the larger airplane, is the Stockholm to Bern in Switzerland. The reason why these were chosen is because these two missions are the ones that closely resemble the missions that the manufacturer published. Yes, so I was talking about the two airplanes analyzed, the Airbus A320 and the ATR. And the two missions here in Sweden, the first one and the largest one from Stockholm to Switzerland. Once you get this information and the length between the distance between the cities using Wolfram language and the entities, you're gonna be able to get some results based on functions that use aircraft performance data. After that, using these results of the mission, how fast you flew, how much time it took you, and the distance, you get that into the direct operating cost models. And bam, you get your total direct operating cost. I searched for 9 models. Those are the ones that are most widely used, available in the literature. We can see on the left that for the small airplane and the short distance, there is a huge disagreement between models. We can only see from the first one and the second one, there is a huge difference. And not only on the estimation on the total cost, but also on the things that each model considers as a direct operating cost. For example, I was mentioning that once you feed this information from the result of the mission, you will be able to get the estimation of 9 different models for the total operating cost. And we can see how much they differ between themselves. For example, the first one and the second one, they are on the bars from the first image. There's a big disagreement. So whenever you see on the literature, on the magazines, that this new airplane is gonna be so much cheaper than what's existing, electric, hybrid, electric, hydrogen, the question you need to ask is, according to which model? There are huge differences. On the second part, for the larger airplane and the longer distance, okay, the median and the average are quite closer, so there is a bit of better agreement between themselves. But we need to consider this whenever we are doing this analysis. If we normalize the results, because we are comparing big airplanes, small airplanes, long distance and small distance, the industry uses the unit cost, which is how much it costs to travel one seat, 1 kilometer. This one you can apply to any airplane, big or small. And then you get this kind of normalized result in dollars per seat kilometer. The same pattern on the first airplane, small airplane, short mission, it's going to be, there's a huge disagreement. On the second one, there is a better agreement. Now let's compare this with the published data. The program actually searches for the example in the first, the ownership costs. It searches for the method that gets the closest one to what ATR is publishing the value. And then we see the difference in percentage, just 1%. So actually, if you pick the best of the best, we get this comparison. The first bar is the estimation, and the second bar is what's published from the manufacturer. So the disagreement is not huge. There is from 12 to 20% of difference between the model and the estimation. And we can also do some break-even cost analysis. For example, each square is a model, and it will tell you how much you need to charge your passenger per kilometer flown to actually achieve a break-even operation. And we see that the models, all of them behave quite different. On the x-axis, we have the length, and on the y-axis, we have, again, this cost per passenger kilometer. Each of the lines is how full your airplane is. Of course, the more empty, the more expensive, which is one concept called the economies of transport. The fuller it is, the least cost per passenger you're going to have to get. Awesome. Yeah, this image is quite heavy, so we can see why the notebook is taking a bit to respond. In the meantime, I can tell you a little bit of the extra things I wanted to show. One you're going to see later on a little bit on the heat map relating the total operating cost with the design parameters. That one helps a lot the design engineer when you see, for example, of course, the number of engines is going to be more expensive to operate than an airplane that has less. And afterwards, a little bit on the data science that was done using real life data of a Swedish regional airline that is quite interesting, in which transforming the text from a .csv into Wolfram entities, we can analyze the whole network and finally get with some costs of the whole operation of the airline. So that would be quite interesting if I can show it. But yes, I do have some back up. This is the heat map I was showing. Because of the PDF resolution, the resolution is not that great, but we can see how the number of engines is actually a lot more. It has a direct impact on the total operating cost of the airplane. This really helps you as a designer, which is my background, aeronautical engineering, to see what you should focus on more. And here, the Swedish regional airline, just really quick. The information was gotten from flight radar into a CSV, then sorted from origin destination. You get the flight hours and then a complete map, as I was telling you. From the beginning, you get this information, this kind of raw, and this is already when you have already processed it. So this once this Stockholm and Visby are already Wolfram entities. So you can do whatever you want with them. And that's how actually the research is being done to see the whole operation of the airplanes. Not only that, you can of course sort by the operation by the tail number. If you want to see a single airplane, you can see if it's domestic or international. For example, this is just domestic, and this would be of course domestic and international. But if we couple this, the existing flight network with the direct operating cost models, then you will be able to get an estimate over here of the whole cost of operating your regional airline. This will give you a lot of insights about, for example, us that we are doing some research on sustainable aviation, about what is about, for example, the cost to beat, since these models only work for conventional airplanes. And you can also do some analysis on the flight routes For example, the bars indicate how much the operation is done. So Braathens Airlines flew a lot, the Stockholm Visby, which we see by the red line, which indicates distance, that is quite short. So this also, again, gives a lot of insight for the aircraft designer. Maybe the electric airplane and the hydrogen airplane, you don't really want to design them just to fly as far as you can. Maybe smaller ranges will be enough to operate the most transited route from this airline. Again, this is real data. And finally, just as this is more like as a nice to know. Does this really impact the ticket I pay? I'm talking you as a traveler, you that log online and try to get a ticket. The answer is not as much as you would expect. The price of your ticket is determined by the demand on the city pairs, not only by the cost. What does this mean? That if you fly from Stockholm to Mexico City, which is the purple line here in the map, that might be more expensive than flying from Stockholm to Cancun, doing a layover through Mexico City. This, of course, doesn't make the minimum sense if you consider the cost, but the price is gotten here based on the demand from the Stockholm Cancun route, which is the orange dashed line that you can see in the map. So of course, this happens more often than what you believe, but airlines do a really good job in hiding it. So you can spend a lot of time searching on whatever internet platform you prefer. You might eventually come up with a nice deal and then just not take the last flight. But of course, this is not always the case. And why does this happen? Because there is a lot of other things going on behind that do not have to do with cost and maybe marketing. Maybe this route has a lot to do with demand. Maybe the airline is trying to fly this airplane to keep the airport slots, the right to use the airport. Maybe it's flying empty airplanes as a competing strategy so that the competing airline loses money. Of course, there is a lot of ethics, then they get involved, and sustainability problems. But in the end, this is the way it is. And therefore, the conclusion that we can take is that from the cost, the one that involves all the models that I've been speaking of, you cannot really infer the price of how much it will cost you as a client to buy the tickets, nor the other way around. If you go online and you search for the Mexico Stockholm flight, it's difficult and not recommended to try to infer the cost from the price. And that brings me to the what's next, the implementation using Wolfram System Modeler. Because yes, these models, if we see the green line, the fuel is constant to speed, and that doesn't really make sense. Even when we drive a car, the faster we go, the more fuel we consume. The models cannot capture it because everything that's complex from aeronautical engineering, drag, performance, that's embedded in this function. That we can get using the aircraft library from Wolfram System Modeler. And then we can actually couple with these DOC models and try to design for optimal cost. This brings me to the conclusions. The DOC models differ on short distances and small airplanes, regional aviation. Whenever you see these electric airplanes, handle the information with caution whenever they claim that the price is really low. It's very model dependent. Nevertheless, if you do the math right, you can expect a 20 to 12% difference between the model and the published data. This also brings insights on why the 4-engine aircrafts are dying. The big A380, that one is retired much more before than what the engineers believed. And there is also this need that I was speaking of, coupling these models to higher fidelity tools like the Wolfram System Modeler aircraft library. And finally, so that you know, the price in which you get your airplane ticket not only depends on costs. There's a lot of stuff involved there behind that obeys more marketing than actual costs. And you don't need to be a coding expert to use the Wolfram language, which was my case. It's quite intuitive and really nice to follow. And with this, I just present a bit on the references and leave the floor open to any questions. So I have a question here. Is the system modeler required for those cost estimations? Would Mathematica be good enough? Yes, if you consider the cost estimations only using the models, Mathematica is the best tool. Actually, everything you saw today is only using Wolfram Mathematica. If you want to couple this with design, if you want to get the whole picture and couple it to the flying airplanes and missions and fuel consumption, then it's a good idea to get System Modeler involved. But again, this is more like as a research that is being performed so far. So hopefully in the next versions, there's going to be some stuff about that. But no, Mathematica is more than enough for you to start crunching the numbers on these models. Awesome. So if there's no more questions, there's nothing else that I can say but to thank really for the attendance today, a little bit on the research that's been performed, that's hopefully going to be published in high quality congresses in aeronautical aviation, sciences and research. And the Wolfram language has been shown to be a great tool into analyzing this. The same with a system modeler. So take a look to those two and we'll see each other around. Thank you so much, and thanks for all the staff that's working behind the screens to make this conference possible.